what is the electric charge and what is the conservation of charge, quantization of charge, and the Coulomb's law also, the force experienced by a charge when it is surrounded by other charges. So when the two forces, when the two like charges, they are kept near each other, they repel each other, we discussed this, and unlike charges, they are attracting each other. So now we should discuss why this happens. So this is because of the creation of the electric field. So this is we are going to discuss what is the electric field. And before doing this, let me remind you that if you like this video, then please share and subscribe the channel. So you know that when two charges, they are kept near each other at a distance r, then this one is applying the force on this attractive force, attracting in this direction, and this is attracting it in this direction. So the force of attraction, both having opposite directions but same force, that is equal to 1 upon 4 pi epsilon naught q divided by r square. Now we have a parameter, or we have the electric field equal to the force applied. So if you divide this force by any of the charge, so if I take this charge, it is kept here, and we have another charge which is brought near to this. So when it is at a distance r from this charge, then the electric field is given by force acting on a unit charge kept near to this charge. So this is equal to 1 upon 4 pi epsilon naught q by r square. This is how we define the electric field. So electric field means there are two terms. One is electric field, other is electric field intensity. This is the electric field intensity. What is electric field? We can say that electric field is the region in which the effect of a charge is felt. So when we have an electric charge kept at some point, so it is producing the electric field, means it is making its appearance being felt by another charges. So when we bring another charge close to it, so it is applying a force on that charge. Obviously that charge is also applying a force on this charge, but we are talking about this charge only. So how is the force being applied? This is through the creation of the electric field. So you can say that this is a phenomena. So the charge produces the electric field, and how do we define the strength or the intensity of electric field? That is equal to the force acting on a unit test charge which is kept at a certain distance from the charge, for which we are defining the electric field intensity. So here if I take this as a unit test charge, and this is the charge for which we are defining the electric field intensity, and they are at certain distance r, then we define the electric field due to this, the field intensity due to this is F by Q 1 upon 4 pi epsilon 0 Q by r square. So you can see that for a given charge, the electric field is proportional to 1 by r square, and this is a vector, the direction of which is outside of the charge if you have a positive charge. Suppose we have a positive charge here, then the field intensity is shown here by the lines going out of this positive charge. They show the intensity. And if I have a negative charge, then field intensity is shown by the lines which are entering into the charge. And these lines are shown because of the force applied by another charge on this charge. If they are the like charges, then this charge, if a like charge plus q or small plus small q is kept near this, then it will be applying a repulsive force on that, and so these lines, these show the repulsive force. If you have a negative charge, and if you keep a test charge which is positive near this, then this charge is going to attract that one, and the lines coming into this, they show the force of attraction. So this is how we define the electric field intensity, and this is also defined as the electric field lines passing through a given area at any time. Given area means area of cross section at any time. This is how we define the electric field lines or intensity of the electric field. So you know that in vector form F is 1 upon 4 pi epsilon 0 Q into, suppose I keep a test charge Q naught near this charge Q. So Q into Q naught divided by R square in the direction of the unit vector R. When the two charges they are separated, or let us take this as Q only, Q and Q as I have shown here. And on this will be applying a force in this direction. So we define E electric field intensity as equal to the force per unit of the charge, F divided by Q, which is 1 upon 4 pi epsilon 0 Q unit vector R by R square, and you know that unit vector is vector R upon magnitude of this. So E is also defined as equal to 1 upon 4 pi epsilon 0 Q upon R cube into vector. You can write this in the vector form. So its unit is here F by Q, so the unit is Newton per Coulomb, and intensity of this is shown by the help of these lines. So they are radiating in outward direction if you have a positive charge and coming into a negative charge. So you can have two charges also at the same time kept near to each other. If they are positive, they will repel each other, and if they are negative both, then they will repel, and unlike charges are going to attract each other. So this is known as a dipole. One positive, and if I have one negative charge, then this is called the electric dipole. And we will be discussing this separately, what is a dipole. And let me give you an example here. The structure of water molecule HHO. You have studied this in the 11th class chemistry, that this is a dipole. How this is a dipole? What is the this hybridization? This is having sp3 hybridization. The oxygen is having two electron pairs which are unused on this unbonded electron pairs, and one are shared here, each with hydrogen atom. So this is the one of the most electronegative atoms, oxygen, and hydrogen is electropositive. So it is what it is going to do is the oxygen atom, it is attracting the electron pair which is shared here between hydrogen and oxygen, and same here. So we have the dipole moments created on this side and on this side. Dipole, the two charges q and minus q separated by a distance d. So dipole moment is equal to the product of charge multiplied by the distance. So here we have one dipole moment, and here we have the other dipole moment, two dipoles. As a result of this, there are two dipole moments, and the resultant of these will be added vectorially to get the dipole moment. This is known as the dipole, which we are going to discuss later on. Now let us discuss about the properties of these lines which show the strength of the electric field. So these lines electric field line, the first thing is that they are continuous curves. They are continuous curves, and they start from positively charged body and end at a negatively charged body. and they do not exist inside the body. No existence inside a body. So they are only above the surface. Their existence is above the surface of a body only. Here by body I mean to say a charged body. So there is no existence of electric field lines inside a charged body, and that you will understand when we discuss the Gauss's theorem. So electric field lines, they are continuous but do not form closed loops as is done by magnetic field lines. No closed loops are formed here. And also, if you have a single charge, then field lines, they may start or end at infinity. For example, for a single positive charge, the field lines, they would start from the charge and end at the infinity. This is a positive charge, start here and at infinity. If you have a negative charge, they start at infinity and end at the charge. So continuous, no break, but do not form the closed loop as in case of a magnetic field lines or curves. Now they do not cross each other at any point. Why? Because at any point, if I take this as the line and I draw the tangent here, this shows the direction of electric field. So at this point there will be two directions of electric field, which is not possible. So they do not cross each other, never. And if you have two charges having unequal values q1 and q2, q1 is greater than q2, in this case the lines of field we can show like this. The gap between these curves, this shows us the intensity of the field produced by a charge. The higher the value of charge, the higher is the intensity of field. So in between these two, we will be having a point, this point, where the intensity produced by the two charges, intensity of the electric fields, will be same but in opposite direction. So here you will find that the net intensity of the electric field is 0, and so this is called a neutral point. So at neutral point, P is neutral point. The electric field intensity produced by Q1 equal to that produced by Q2 here, and they are in opposite direction, magnitudes are same. So this will be lying always closer to the smaller charge. So if Q2 is smaller, this point will be lying closer to the smaller charge. And if you have two charges, when they are similar charges, then you will find that these electric field intensity lines, they will be applying the pressure on each other. So we can say that electric field lines, they contract longitudinally because of attraction between the unlike charges. They contract longitudinally because there is attraction. And similarly, we can say that electric field lines, they exert a lateral pressure on account of repulsion. They apply lateral pressure on each other. because of repulsion. Among same charges. I should use the word between. So these are the properties of the electric field lines. And I told you about the dipole moment. So the dipole moment, if we have two charges, one plus and another minus, separated by a distance 2a apart, then dipole moment is the product of the charges. We have two equal charges here multiplied by the distance between them, and its direction is given by, this is a vector, negative to positive. This is the direction. So if you have a molecule of water, this is negative positive, so dipole moment of this one is given in this direction, whereas the dipole moment of second one is in this direction, and they have certain angle between them. So the resultant of these two dipole moments is the net dipole moment in this direction. This you can find by using the vector sum of these two moments. This is how we define the dipole moment. Dipole moment is Coulomb meter. So this is about the electric field and its intensity. So now we will be calculating the electric field intensity due to two charges, or due to a charge which is kept with another charge. Let us find this. So we have a charge, this is minus q and this is plus q. This is an electric dipole. So we have to find the electric field intensity at a point P at a certain distance. Suppose we have this point P here. The distance between these two is 2a, and this is the center of this dipole. From this, it is lying at a distance x. So we have to find the electric field intensity at this point. So what we do is, first of all, find the intensity due to this charge minus q at this point P, and then due to charge plus q, and then vectorially we sum each other. So the distance of minus q from this point is x, plus this is half of the distance. This is given by x plus a, and from this distance is x minus a. So having defined this point P with respect to the two charges, let us find the electric field intensity here. So electric field intensity at point P due to charge q, this is a positive charge, so field produced by this will be in direction away from the point P. So this is EQ. And similarly, this is the negative charge, so field intensity will be in this direction, E of minus q for this. So we will add these two and find the total value of the field intensity here. Let us write the magnitude of EQ here at this point. Let this point be A, this is B, and this is O. So this is 1 upon 4 pi epsilon 0 Q divided by the distance, this is x minus a whole square, and this is towards the left direction. So arrow means in this right direction, and E due to minus q is 1 upon 4 pi epsilon 0 q divided by x plus a whole square, means with respect to this towards left. So they are in opposite direction, means at an angle 180 degree to each other. This angle is 180 degree, E minus q. So if you sum them vectorially, then E at point P is equal to EQ and minus of E of minus q. Means you have to sum them. So if you apply the rule, under root of EQ square plus E minus q square plus 2 EQ E minus q cos of 180 degree, this will give you EQ minus E of minus q. So putting the values here, 1 upon 4 pi epsilon 0 into q, that will be taken common. So you can see here, this is the value of electric field at P, and the direction will be towards right, because this is more than this. So the direction will be, net field will be in the right direction, rightward direction. So you can simplify this. We can write 2aq into x upon x square minus a square whole square. Suppose we have x is much larger than a. In that case, x square minus a square whole square is approximately equal to x to the power 4. So this is equal to 1 upon 4 pi epsilon 0, and here 2a into q is equal to p, the dipole moment magnitude. So 2px by x4. So 1 upon 4 pi epsilon 0 2p divided by x cube in the direction towards right. So you can see here E is proportional to 1 by x cube for a dipole, the length of which is 2a, and x is the distance of the point where we have to find the net electric field from the center of the dipole. This is the magnitude. So I can write in vector E is 1 upon 4 pi epsilon 0 2p divided by x cube. This is how we find the electric field due to a dipole. Similarly, we can find the electric field at a point which is on the equatorial line of the electric dipole. This is called the axial position. And now we can find with respect to a point on equatorial position. This is our dipole, charges minus q and plus q, and the perpendicular bisector of this is called equatorial position with respect to this. All points lying on this are called equatorial. So let us take a point here, point P. and this distance is, say, x. OP is equal to x. Let us join A with P and B with P. So electric field produced by minus Q will be in this direction, E of minus Q, and that by the positive charge will be in this direction. You extend these lines, this line, this is the horizontal line. Suppose this angle is theta. So if you show these two fields, EQ and E of minus Q, then this angle is theta, this is also theta, so this is 90 minus 2 theta. Sorry, 180 minus 2 theta. So this angle will also be 2 theta. So theta, theta. So if you take the components of these two, this one is having cos component in this direction, EQ cos theta, and EQ sin theta. Similarly, this one, E of minus sin theta and E of minus Q cos theta. So the net field here at point P is equal to EQ cos theta plus E of minus Q cos theta, because these two components being E opposite will cancel each other. So E of minus Q here is equal to 1 upon 4 pi epsilon 0 Q divided by AP square, and this is in the direction P to A. And if I write the value of AP here using this triangle AX, so root of A square plus X square. Similarly, we can write for the other one. So this is 1 upon 4 pi epsilon 0 Q upon A square plus X square. The direction remains the same, P to A. If you write this with the unit vector, then you need not write here this direction. And similarly, E due to Q is 1 upon 4 pi epsilon 0 Q upon distance, this PB, which is same, and the direction is from B to P. Now summing up these two, this is equal to EP and EQ are same, 1 upon 4 pi epsilon 0 Q upon A square plus X square into cos theta. 2 into cos theta, because these two are same, so this is 2 EQ cos theta or E minus Q cos theta. So into 2 into cos theta is in this triangle base upon hypotenuse. So this is 1 upon 4 pi epsilon 0 Q into 2A, that is P, divided by A square plus X square to the power 3 by 2. And what is the direction? Direction is parallel to the base at this point in the direction from P towards the left, parallel to the base. This is the direction. If you have the X much greater than A, then E at this point P is 1 upon 4 pi epsilon 0, leaving E here in comparison to X, so this is X cube. So this is P by X cube. Here also you can see it varies proportional to 1 by X cube. So E of, you can write the ratio in the previous case to this case, longitudinal to equilateral, equatorial. The ratio is 2 by 1. So in general, if you have this dipole and you want to find the electric field intensity at a distance x from it, such that this point, when joined with the center of the dipole, is making an angle theta. This point is P. So we can write this with a same formula, 1 upon 4 pi epsilon 0 P root 1 plus, and this formula you can use for both, and you have to put just the value of theta. So root of 1 plus 3 cos square theta, 3 cos square theta divided by x cube. This distance is x. So you can remember this formula. So if you have theta equal to 0 degree, that will be the first case. This point P will be here. So this is longitudinal position, and you will get this as 1 plus 1 into 3, 1 plus 3, 4. So 2p by x cube. If you have theta equal to 90 degree, means this position, this is equatorial. So you can remember this result, and in this case the two components are inclined to each other such that tan alpha is tan theta divided by 2. So if you take this point here, you will be having two components of the electric field. One is along this and other is normal to this. The resultant will be like this. This angle is alpha and this angle is theta. So these two components are inclined. The resultant is inclined to this component along this line, joining midpoint with the point P at an angle alpha. So the angle alpha is given by tan inverse of tan theta divided by 2. So even here you can write in this direction, one of the component is given by 1 upon 4 pi epsilon 0 p sin theta divided by 4 pi epsilon 0 r cube, and I am giving the derivation of only these two. This is just for your remembering. This also has a proof but not given in your book. So at some other place I will provide you the proof for this. Here I am just writing the value so that you can remember the formula. And E2 is 1 upon 4 pi epsilon 0 2p cos theta divided by r cube. These are the two components of the electric field, and when you vectorially sum these two, you will get this formula. So if you have theta equal to 90 degree, in that case you will find that tan alpha is tan 90 divided by 2. That means alpha will also be equal to 90 degree. That means theta is 90, you will get this position. So alpha in that case, the resultant will be making with this line in this direction, and this angle is 90 degree. So this is how you can find the electric field due to a dipole in the two positions. So after this we will be discussing how to find the electric field due to a charge ring, due to a charge plate, and some other objects at a certain point. So this is all for today. Thank you very much.